Now we're going to make a transition from long-term changes in climate, long-term changes in atmospheric chemistry and their influence on the Earth, and focus on more recent events. In this lecture, we're going to focus on the Pleistocene glaciations and how they ultimately make the world that we live in today, how they make us what we are today, what we eat today, what we drink today, where we live today, all result ultimately from the Pleistocene glaciations. Now, this starts with the work of Louis Agassiz in the 1840s, a Swiss geologist, that began to question the Earth's climate history, and he focused principally on glaciation. Those were the most dramatic examples of climate change present in Europe at the time. Unfortunately, until about 100 years later, in 1947, there was no way to calculate specifically what temperatures were. In 1947, we're coming out of World War II, and we gained a lot of isotope information. We had a nuclear program in the United States to develop atomic weapons that hired the best physicists, chemists, and isotope chemists in the world. In their conversations and in the latest breaking scientific advances, Urey came upon the idea of using isotope chemistry of carbonates to determine temperatures in the past. He published this in a famous paper, The Thermodynamic Properties of Isotopic Substances. And in this paper, he calculates the temperature dependence of oxygen isotope fractionation between calcium carbonate and water and proposes an isotopic paleothermometer, the use of carbonates as a temperature measure. One of his early students, a postdoctoral fellow named Sam Epstein from Manitoba, and several of his students came up with the idea of growing mollusks, growing clams in water at different temperatures. This was published in a paper in 1953 by Epstein and others. And in this paper, they found this relationship. The delta value, ratio of oxygen 18 to oxygen 16, between one phase and another is equivalent to the isotope value of the calcite minus the isotope value of the water in this format. So this is a paleotemperature equation. If we know 2 of 3 unknowns, we can calculate the third. This is what they generated in this paper. So growing clams at a number of different temperatures from 30 degrees down to around, I think, 6 or 7 degrees was the lowest temperature. They measured the ratio of oxygen 18 to oxygen 16 in that clamshell material and plotted that on a line relating the isotope value of the carbonate to the temperature at which the carbonate was produced. So this led to the formulation of a record of climate change in deep sea sediment. It's a bit weird that the best records of climate change are in the ocean. And one of the reasons is that every subsequent glacial episode destroys the continental record of the previous glacial episode if it exceeds the size of that previous glacial episode. So if our next glacial period is more severe than our last one, it would essentially rub away all of the records left behind from the last glacial period, which ended around 20,000 years ago. We see the disappearance of our charismatic megafauna at the end of this last glacial episode. And we have a human for scale, some of our favorites, woolly rhino, a very large version of a tapir. We have a very large dog, and our giant ground sloth. Deep sea sediment isn't disturbed by glaciation unless it's near shore sediment. And if it's near shore sediment, it's usually not deep sea sediment. So we learned a lot about Pleistocene glaciation in North America and Europe from looking at moraines, looking at fossils, artwork, things that people leave behind give us some clues. But there were a lot of questions remaining, including when did all these things happen? There was no chronology. What caused these things to happen? What were the temperatures? How did they change? What kind of ice volume are we talking about? When we talk about ice volume, it's easy to see where the ice was, but we can't tell how thick the ice was necessarily. So the question of chronology or timing has been resolved somewhat through isotopic studies of deep sea biogenic sediment, somewhat. Now, there are a number of difficulties, a number of problems with what we're going to talk about for the next few minutes, but we're just going to roll with it for the time being. The principles involved in isotope paleoclimatology or isotope sclerochronology are fairly straightforward once you get a handle on what some of this terminology means. The isotope record of carbonate that's produced by organisms should provide a record of ancient ocean temperatures because the fractionation of oxygen-16 relative to oxygen-18 between carbonate and water is temperature dependent. The value is determined by the temperature. Now, when it comes down to reality, it gets a little bit more complicated because the isotope value of the carbonate is dependent not only upon the temperature, but also the isotope value of the water the organism is living in, and any vital effects that the organism may impart on the fractionation. This is a physiological, biochemical kind of effect on the isotope value. So we need to have an idea how each organism responds and produces carbonate. Here we have a couple examples. This is a speleothem, or cave thing. It's a stalactite that's been cut in half. You can see the accumulation of carbonate represented by these bands. Same thing goes for this brain coral, where you can see the age of the corallites as you move across the organism. And this is a fish otolith, probably looks like a cod from the North Atlantic. And we can see clearly years represented within the fish's life. Now, if we could take these things apart, and now we could get a temperature record throughout the animal's life, whether it's a fish or a coral, or in the case of a cave, a abiotic precipitation of calcium carbonate. So this early record was developed by Urey and Epstein. Urey first proposing it in the 40s, then Epstein jumping on board quickly in the early 50s. And at the same time, we have Cesare Emiliani at the University of Chicago. So all three of these guys ended up in Chicago working on these isotope problems. Now, I haven't met Urey. He died in the 80s. Epstein offered me a job after I gave a talk in Cincinnati once, and Emiliani told me I was crazy for some of the things I was proposing. Many of Emiliani's findings are still valid today. Some of his conclusions were that the last glacial cycle ended about 16,000 years ago. That's more or less correct. He determined that temperature increased steadily from that time until about 6,000 years ago. That's more or less correct. Critically, he noted that there were 14 other glacial interglacial cycles that were global events, not just high latitude events, global events. And this means that there was cooling even in the subtropics. He concluded that this variability in climate was related to the Earth's orbital parameters. What did he see? Well, this is what he saw. This variability in isotope chemistry was converted using Epstein's equation into temperature. So here we see temperatures swinging from relatively high, warm temperatures, to low temperatures. High temperatures, low temperatures, high temperatures, low temperatures, over and over again, 14 times. Up to this point, we thought there were 4 glaciations. And again, we thought there were 4 glaciations because they erased the previous glaciations. Emiliani had this whole field basically to himself until about 1970. So a good 15 years to work in this really cool field, doing lots of cool stuff before anyone else caught on to how it was done and what it meant. So he got a lot of things right. And other people noticed the success he was having, the value of this approach, and they jumped on board. And I jumped on board in 1990, not for this particular reason, but ultimately got back to this reason. So one of the primary improvements between 1955 and today is the development of timescales that are run by chemistry. So in this case, we have beryllium-10, thorium isotopes, uranium-lead, carbon-14. All of these have improved. Our ability to measure them has improved. Our understanding of them has improved. So our dates are getting better as time goes on. In the 50s, Emiliani only had carbon-14 dating available. So this is something that's only good going back for 50,000 years or so. And at that time, not even that far back, anything older than that had to be extrapolated back in time, saying if it takes 10,000 years to accumulate 1 meter of sediment, we have 30 meters of sediment, it should take 30 times that amount of time. So that's the way extrapolation was working until we got this chemistry under control. So one of the questions was, how much of the variability in carbonate sediment isotope values is due to temperature change, and how much is due to a change in the isotope value of the seawater? Now, early on, it became apparent that the dramatic expansion of these large ice sheets would change the isotope chemistry of the ocean. So we're taking a bunch of oxygen 16s, tossing them up onto a continent in the form of a giant pile of ice that's leaving more oxygen 18s behind. So the isotope value of the ocean goes up when ice accumulation on continents goes up. So today we can look at the isotope values of Greenland ice. We see that they're minus 30 to minus 40 relative to Vienna standard mean ocean water. This is just a standard that was developed to relate one thing to another. And values can be as low as minus 50, actually around minus 55 at the South Pole for Antarctic ice. So if we know the volume and the isotope value, it's a simple budget calculation. This much of that much of this. If precise values can be determined for ice and the precise volume of the ice can be determined, it would be easy to do this budget. Today we have a volume of continental ice that's 27.5 times 10 to the 6 cubic kilometers. Volume of the ocean, much, much bigger. Assuming glacial ice has a mean oxygen 18O value of minus 30, we can calculate the 18O value of the hydrosphere as 0.6. At the height of the Wisconsin glaciation, the volume of glacial ice is thought to have increased by 42 times 10 to the 6th, corresponding to a lowering of sea level of about 125 meters. If the 18O value of ice was the same then as now, again about minus 30, we can calculate that the delta 18O value of the ocean would have increased by 1.6 per mil. This is like percent, which means per 100. This is per 1,000 per mil. And we can see that illustrated here. During a glacial period, we put a big pile of minus 30 ice on the continent. That leaves more oxygen 18 behind in the ocean. When that ice melts, we go into an interglacial. We have still a significant amount of ice in Greenland and Antarctica, but not as much. And as a result, we get to the oxygen isotope value of the ocean today, which we have decided is going to have a value of 0. So it's now assumed that the ocean changes by about 1.5 per mil between glacial and interglacial periods. The exact amount is something people argue about. Now, people started measuring isotope values of deep sea sediment from all over the world. And because it's very expensive and many times impossible to get good chronology on some of these cores, you have to come up with a time scale. So what they do is a bit like cheating. You just take your isotope values and you stack them up. When you have a high point here, you assume it happened at the same time as the high point in another core. And you do this over and over again through the whole core, and this is called tuning. If it was a student taking an exam with the help of other students, it would be called cheating. So in this case, scientists are doing it, so it's stacking or tuning as opposed to sharing information, which would be cheating. And subsequently, given enough time, in this case 50, 60 years of time, people went crazy and they started giving all kinds of names to different periods of time as measured in ocean cores. So we have stages and substages and terminations, 7A, 7B, 7C, E, D, A. It's troubling to me. I would rather just stick to time. Okay, what's driving all this? What is the cause of these recent glaciations? An examination of the global curve shows a periodicity of about 100,000 years. Now that's because they've been tuned to 100,000 years. That's problematic. The same periodicity was apparent in Emiliani's work, and it led to him to conclude that the glacial interglacial cycles were due to variability in the Earth's orbital parameters. These are now known as Milankovitch cycles after Milankovitch, a Serb who argued in the early part of the 20th century, actually during World War I, that ice ages were caused by this orbital variability. The three parameters of most interest here are eccentricity, obliquity, and precession. So Milankovitch was a strong and early proponent of the idea of orbital variability influencing Earth's climate, but it wasn't his idea. It came about from another man named James Kroll of Scotland, and he suggested it many, many decades, a half a century before Milankovitch. And he also published a few papers. Now he's kind of a goodwill hunting of Scotland in the early 1800s. He was born on a farm, self-educated. He taught himself physics and astronomy. By the time he was 16, he became a wheelwright. And then, because of health problems, he became a tea merchant. So he ran a tea shop in Moray. In the 1850s, he managed a hotel and then became an insurance agent. And in 1859, this is important, he became caretaker at a museum in Glasgow. This is important because he used his job to gain access to books. There was no internet at the time, so if you're a poor guy like he was, well, not poor, but not wealthy by any means, you need to have access to information. He corresponded with Charles Lyell on links between ice ages and variations in the Earth's orbit. This led to a position in the Edinburgh office of the Geological Survey of Scotland as keeper of maps and correspondence, where the director encouraged his research. He published a number of books and papers which were really groundbreaking, including Climate and Time in their geological relations. In 1875, he talked with Darwin on erosion by rivers. Darwin was a geologist by training. He was on the Beagle, traveling around the world, making his discoveries on evolution, at least formulating his ideas, while he was supposed to be looking for silver. So he was shirking his duties as a geologist to develop the idea of evolution. In 1876, Croll was elected Fellow of the Royal Society, and he was given an honorary degree by the University of St. Andrews. He retired in 1880 as his health was declining further, and he died in 1890. Kind of a sad ending to a bright guy. Now this brings us to another bright guy. This is Milankovitch, born in 1879, so just prior to Kroll's death, and he lived till the 1950s, almost 1960s. He was a Serb who was homeschooled. Like Kroll, bad health kept him home. Once he began to attend high school, he became the best student in the school. In fact, he was the best student in Serbia, which was part of the Austro-Hungarian Empire at the time. But he was encouraged by his family to get an agricultural degree so that he could maintain their property, their land holdings. He wanted to study electrical engineering, but that degree wasn't offered in Vienna where he was living, so he went into bridge engineering, earning his PhD at the age of 25 for Beitrag zur Theorie der Druckkurven, the theory of bridge curves, essentially. At the beginning of 1905, he became employed as an engineer working in Vienna, and he ended up designing lots of Belgrade, Yugoslavia today. Well, Yugoslavia in the 90s, Serbia today. So he was offered a position at the University of Belgrade in mathematics. He got married. Right after his wedding, he was arrested as a citizen of Serbia and sent to prison in Karlovac, famous now for its beer, and later in Osijek. His family got him released as long as he agreed to stay away from the Serbian border. He got sent to Budapest, where he had to report to the police station every day during the rest of the First World War. While he was sort of penned away in Budapest, he devoted his time to these Milankovitch cycles. And by the end of the war, he finished a monograph that was published in 1920. It's the theory of the phenomena of the thermal characteristics of solar radiation. That's illustrated here with eccentricity being the expansion and contraction of the ovalness, or the eccentricity of the Earth's orbit around the sun. Obliquity is variability in tilt, sort of a wobble between 21.5 degrees and 24.5 degrees of tilt. And then precession, where the Earth is located relative to a specific period of time. In 2020, the Earth is closest to the sun in January. As a result, Northern Hemisphere winters and Southern Hemisphere summers are somewhat milder than they would be otherwise. Imagine that. For a given latitude and season, precession will result in about a 5% difference in insolation. While the Earth's orbit is only slightly elliptical and variations in eccentricity are small, these variations are magnified because insolation varies with the inverse square of the Earth-Sun distance. Variation in tilt approximates a simple sinusoidal function with a period of 41,000 years. Variation in eccentricity can be approximately described as having a period of 100,000 years, but really variation in eccentricity is more complex, with periods of 123,000 years, 85,000 years, 58,000 years, while variability in precession has periodicities of 23 and 18,000 years. So Emiliani, early on in the 1950s, suspected that these variations in the Earth's orbit are going to be related to variations in the delta 18O value of deep sea sediment. Now, when we look at continents, things get a little more difficult. Climate change leaves a record on continents as it does in the deep sea, but on the continents, the complications are greater. Record may be stored as ice or carbonate precipitated from water, either in a clamshell that's deposited in sediment or a speleothem which precipitates carbonate as water is dripping from it in a cave.